Hi, my name is Lucas Weintraub, and today we're going to prove the law of cosines. Usually in your Algebra 2 or trig classes, you're going to be shown formulas like this, and you have no idea where they come from, and so that's what we're doing today. I'm going to show you where these weird formulas come from. So the formula for the law of cosines is a squared is equal to b squared plus c squared minus 2bc cosine a. In other words, if this was kind of like the hypotenuse of a triangle that is not a right triangle, then it's equal to the squares of the legs minus double the product of those legs times cosine of the angle opposite A. So that's a lot to take in, and that's why I want to show you proof of it, because sometimes it might be hard to remember, but this way it will click in your head a little more. So the idea for this proof is to find a squared by drawing a right triangle and finding the values of the sides of that triangle. And the reason why is because the law of cosines is similar to the Pythagorean theorem. They're basically the same, but just one little thing tweaked, and it's actually this thing right here. So if we can figure out why that is, then knowing the law of cosines is going to be easier to remember. And the reason why I want to draw a right triangle is because the Pythagorean theorem is all about right triangles. It's about finding the sides of a triangle with an angle that is 90 degrees. So our first case is going to be when an angle like this is acute. So how would you find the value of A if you knew BC? Or how would you find C if you knew B and A? You can't just use the Pythagorean theorem because this angle right here is not 90 degrees. But we need to use the Pythagorean theorem somewhere because that can help us find the rest of the sides. So to use the Pythagorean theorem, we need to use a right triangle. But there is no right triangle, so how do we do it? Well, we make one. So we're going to draw an altitude right here, a straight line, because drawing an altitude from one point to the side of another triangle, or the side of a triangle, the angle it makes will be 90 degrees, and that's exactly what we need. So this right here is 90 degrees, and now we have A right here, that's the hypotenuse, and we want to figure out what these sides are. So let's start off with this one. So if this angle is A, this length right here is going to be B times the sine of A. And this length right here is going to be B times the cosine of A. And that's because of trig rules. And if you are confused about that, I recommend that you watch videos on sine and cosine and my video about the unit circle. Now that we have this side and we know the whole thing, this little part, this part here is going to be, I'm going to draw like that. This is going to be C minus this smaller part. So it's going to be C minus B times cosine of A. So now that we have the two sides and the hypotenuse, we can express A in terms of B, C, and cosines. So the Pythagorean theorem states that it's going to be the square of the hypotenuse will be the sum of the squares, or sum of the squares of the legs. So that's going to be this quantity squared plus this quantity squared. That's what we found earlier. Now, if we expand this, we get B squared sine squared of A plus C squared minus 2BC plus B squared cosine A. Oh wait, actually that's wrong. 2BC cosine of A plus B squared cosine squared A. So this is already looking kind of promising because we have the weird term that was different from the Pythagorean theorem. So now we just need to simplify this. So we have two terms like this. We have cosine squared and a sine squared, and they're added together, and using our Pythagorean identities, we can rearrange this and factor like so. There's quite a lot to write. So we just move this over here. And what that did is now we have these together, and we get sine squared A plus cosine squared A plus the rest. The rest is this, by the way. And sine squared A plus cosine squared A is going to be 1, because sine squared of any angle plus cosine squared of the same angle is going to be 1. So what we're left with is b squared plus this thing in blank, which is c squared minus 2b cosine, no, 2b c times cosine of a. And all of that is equal to a squared. So now we've proven the law of cosines for acute triangles. Now we're going to do the same for obtuse triangles. So we have a similar triangle here with the same labels, and now the angle is obtuse. It's this triangle here. And I've already started drawing the right triangle that we need to solve it. And it's going to be a similar procedure, just using some tricks. So a squared is going to be the same as the sum of the squares of these legs. So we're just going to have to find the value of these legs. This value right here is going to be b times sine of 180 minus a, because it's the angle a. Actually, I'm going to write that over here so that's clearer. And then this value right here is going to be b times cosine of 180 minus a. But we don't want this in terms of 180 minus a. That angle is kind of weird. We want it just in a. And thankfully there are rules that tell us that the sine of 180 minus an angle is going to be the same as just the sine of the angle. And for cosine, the cosine of 180 minus an angle is going to be the same as negative the cosine of that angle. So now, this whole a squared is going to be this side plus this whole thing. So it's going to be b times sine of a squared plus c, which is this, plus this. And then all of that squared. So that's the same as a squared. So plus adding a negative is the same as just subtraction. And now we're left with the same equation that we had before, b sine a squared plus c minus b cosine a squared. And so that means it works for obtuse triangles too. Now that is a proof for the law of cosines, and I hope that now it's easier to remember, or now you understand it a little better.